Hello, so we're on page 22 looking at gas equilibrium. So we're going to see a lot of the same things that we saw in our Unit 6 equilibrium way back when, but now we're going to be mostly working with our gases, and we have a few little tweaks with that. The first being that our pressure can be substituted in for molarity in a rice table. This is only going to be the case whenever we have a reaction at constant volume and temperature, because if we have constant volume and temperature, pressure is directly proportional to our moles, and then moles are directly proportional to molarity, so we can substitute pressure in for molarity or for moles in the case of stoichiometry. So let's look at this first example here. We are reacting the noble gas krypton with chlorine gas in a rigid sealed container at a constant temperature. So rigid container means we have a constant volume and we have a constant temperature here. Initially, we are given our partial pressure of krypton and the partial pressure of chlorine. It tells us that this reaction is going to completion. After completion, we only have krypton remaining at 0.4 atmospheres. We're looking for the formula of the compound that's produced. So we're going to do a little stoichiometry or rice little BCA table here. So let's start by looking at our reaction. We have krypton gas reacting with chlorine gas. Called chlorine gas is diatomic. It's one of those Brinkelhoff elements. And we're looking for the formula of the compound that's produced. So we don't really know. We can call it KRXCLY for now. And eventually we're going to figure out what those subscripts X and Y are. That's essentially what the problem's asking us to do. Well, we can't balance this because we don't know what our little formula is there. Well, we know some initial and final values here, so looking at a rice table or BCA table, same thing. We can plug in those partial pressures for moles. We know we started with our 0.85 atmospheres of krypton, and we had 1.35 atmospheres of chlorine. After the reaction went to completion, we had 0.40 atmospheres of our krypton remaining. It doesn't say anything about the chlorine we have remaining. So we're going to assume that there is no chlorine left. If this reaction went to completion and there's no chlorine left, chlorine must have been our limiting reactant. So all of our chlorine reacted, so we know that 1.35 atmospheres of it reacted. If we started with 0.85 krypton and we ended up with 0.40, we know that 0.45 of it reacted. So remember, these atmospheres are directly related to moles. So what this is actually telling me here, that's the ratio of my atmospheres of krypton and chlorine that reacted to each other. And because those are directly proportional, that is also my ratio of the moles of krypton that reacted to the moles of chlorine. Well, now this is kind of looking like an empirical formula problem. I know my krypton and chlorine are reacting in a 0.45 mole to 1.34 mole ratio there, but we need all whole numbers for that ratio. So let's divide both sides by 0.45. If we divide both sides by 0.45, that tells us we have 1 mole of krypton per every 3 moles of Cl2 that reacted. But I don't have Cl2 in my compound. My compound is just Cl. Every 1 mole of krypton, we have 6 moles of just the singular chlorine atoms. So we found that atmospheric ratio that they reacted in. Atmospheres are directly related to moles, so we found our mole ratio they reacted in, and that mole ratio there, once we get it to all whole numbers, becomes the subscripts for our compound. So the compound that we formed here we have 1 Kr per every 6 chlorines. So that's just an example of how we can directly relate our atmospheric partial pressures to moles. So when it comes to equilibrium, we know that we describe that equilibrium position with the equilibrium constant K. That K is described by the law of mass action, which is relating the concentration of products and reactants at equilibrium. Each K value is only true for one given temperature. You change temperature, you change your K value. But Ks are also different depending on if it is a Kc or a Kp. Kc, we use the concentrations of our gas and aqueous compounds that we put into there. Remember, solids and liquids don't go into our equilibrium constant expression. Kp, we plug in pressures. Well, we can only plug in pressures for gases. It's written the same way. It's still products over reactants raised to the power of their coefficient, but it's not concentration of products over reactants for Kp. For Kp, it's the partial pressure of products over reactants raised to the power of their coefficients. So we see that in our general little equation here. Notice how the partial pressure is represented. We use that capital P to represent partial pressure. The subscript is for what compound it's formed. So this is a partial pressure of C, and then it's raised to the power of its coefficient, that little lowercase c there. When we're using Kp, we do not use brackets. Brackets mean concentration. Kp is written off of partial pressures, so we have to make sure that we're denoting that the right way, using that capital P. So that capital P is what we want to use for our partial pressures when we're writing out those Kp expressions. So we'll get some practice with that here in a moment, but let's also review another important equilibrium concept first, and that is Le Chatelier's principle. Le Chatelier's principle states that whenever a stress is applied to a system at equilibrium, your equilibrium system is trying to counteract that stress. It's trying to get back to where it was before that change. Sometimes, though, the concentration can never get back to exactly where it was before, so a new equilibrium system is established, or new equilibrium. It's still the same K value if you didn't change the temperature. We just might have slightly different concentrations that we end up with to get that same ratio. Different stresses that could be applied are heat, adding or removing a reactant or a product, changing pressure or volume, adding a catalyst. When we are looking at heat, we must know if our reaction is endo or exothermic. Remember that endothermic reaction means we're absorbing heat, so that heat's going to be on the reactant side. So then we can treat it the same way as if we're adding or removing a reactant whenever we add or remove heat from that system. Your system, if you add something, is going to shift in a way that is trying to use up the excess that you added. Whenever you remove something, your system's trying to get back to where it was, so it needs to go and try and replace what you removed. Whenever it's exothermic, we consider heat to be a product. So if we increase a product, we're going to shift away from it to use up the extra. If we decrease a product or the heat, we're going to shift towards it. So heat and adding or removing your reagents are treated the same way, but for heat, we just have to know if it's endo or exo, so we know if our heat is a product or a reactant. One other thing with adding or removing a reactant, if you add or remove a solid or liquid reactant, there is no effect on the equilibrium. Solids and liquids are not included in that equilibrium constant expression. They do not affect equilibrium. However, if you have a shift due to another stress, you can still produce more of that solid in your shift or use some of it up in that shift. But changing the amount of a solid or liquid is not a stressor. It won't change it. All right, so pressure and volume, that's going to affect our gases. We have to look at our moles of gas. Remember, pressure and volume have an inverse relationship. So increased pressure means we have a decreased volume. So if it says something like we're making the volume of the container smaller, that's increasing our pressure. Well, our system wants to decrease the pressure again. It can decrease the pressure by shifting towards the side with fewer moles of gas. Less gas particles is a lower pressure. So then if we decrease the pressure, your system wants to re-up that pressure, so it's going to shift towards the side. That's going to produce more gas particles, because if we have more molecules, that in turn is going to raise our pressure again. Catalysts, remember, have no effect on the equilibrium position. There is no shift. We're going to, if we're not already at equilibrium, we're going to get to equilibrium faster, and then once we're at equilibrium, our forward and reverse rate will still be equal, but they're just both going to be going faster now. The last stress that we don't have listed on here, be adding an inert gas, so something like a noble gas, which does not react. If it is not part of your equilibrium system, just like those solids and liquids are not part of your equilibrium system, adding or removing them has no effect on the equilibrium system. So we have these shifts, but the equilibrium position remains the same. Your system's shifting to get back to the same equilibrium it was at, which is determined by that value of K. The only exception is if you change your temperature. If you change your temperature, that will in fact change your value of K, and we're going to go and look at and see why over the next couple examples here. So on our first example here, we're looking at this little reaction for the synthesis of our liquid water. We want to write the Kp, and then we're given some of our partial pressures at equilibrium here. So at equilibrium, we have partial pressure of hydrogen and oxygen. We want to go and calculate what that Kp is. Well, let's start by writing that Kp expression. Remember, Kp is based off of the partial pressures, so take a second and write that out. Make sure that you have your partial pressure denoted the correct way. When you have that Kp written out, our numerator is just going to be 1. Our product is a liquid. We don't include liquids in our equilibrium constant expression. And this is over the partial pressure, so we need to make sure we have that capital P, no brackets, because it's not concentration. So that capital means partial pressure. We put the little subscript for our chemical and raise it to the power of their coefficients. Well, then it gives us those partial pressures, so we can just plug those in. They are equilibrium partial pressures, so we can plug them into Kp and solve that out. That's easy. So we got those hydrogen and oxygen partial pressures plugged in. We throw this into a calculator. Those partial pressures had 4 sig figs, so we get to keep 4 sig figs. Remember, K does not have units, so we found that value to be 0.9108. So we want to know if this favors the reactants, products, or neither. Well, when K is equal to 1, that's because products are equal to reactants. This is a little less than 1, so that must mean we favor the reactants. But it's only barely less than 1. So it only slightly favors our reactants. When K is equal to 1, products and reactant concentrations are equal. So barely less than 1, we only have very few more reactants than products. Okay, so let's go on and take a look now at number 2. On number 2, we're given mole fractions of our equilibrium system here. Remember, mole fractions are a ratio for the amount of that gas that we have in our system. So 0.243 out of 1, or 24.3% out of 100, is going to be chlorine. 27.4% of our mixture is oxygen, and 48.3% is the Cl2O5 from the mole. So 24.3% of the moles are chlorine gas. It tells us the total pressure of this system is 3 atmospheres, and we're looking for our Kp. Well, remember we can use mole fractions to find our partial pressures, because if we need to find our Kp, we need to plug in our equilibrium partial pressures. That's what we got to go and find first. Find the partial pressures from the mole fractions, and we'll start with chlorine. We need to take that total pressure of 3 atmospheres, and I know that 24.3%, or multiplied by that ratio form, 0.243, is going to tell us how many moles, what our partial pressure of the chlorine is, and that gives us 0.729 atmospheres. We can go and follow that same procedure for our other 2 gases. So we took that mole fraction time our total to find all of our partial pressures there. Now we can go and plug those into our Kp expression. In that Kp expression, we want to make sure we have partial pressures, big P, raised to the power of their coefficient of our reactants over our products. Now we already found those partial pressures from our mole fractions. Go plug them in. Once we have those plugged in, type this into the calculator, and we find a Kp of 0.0949. So again, less than 1, we're favoring the reactants, but much more so this time since it is not near as close to 1. So in our last example here, we are looking at Le Chatelier's principle using this thermochemical equation that is given to us at the top here. We're only going to look at a few of these together, and I'm going to save the rest of it for practice for you. So for each of the given stresses, we want to know after equilibrium is reestablished, what will be the effect on our moles of oxygen, pressure of oxygen, and our Kp. The first one is increasing the volume of the container. Well, if we increase the volume of the container, volume and pressure are inversely related, so that's going to be decreasing the pressure. When we're changing pressure or volume, we're just looking at moles of gas. Well, my only gas is this oxygen gas on the right side here. So if we decreased our pressure, our system wants to increase the pressure again. It can increase it by producing more moles of gas. So our system is going to shift to the right and produce more moles of gas. If we increase the moles of gas, that's going to increase the pressure. But our pressure is only going to increase to the point that it was at before equilibrium was established. So our pressure of our oxygen gas isn't going to change. We have more moles, but we have more moles in a greater volume until we reach the same pressure that we had before. So let's see how Kp is going to change. Let's go ahead and write out that Kp expression real quick first. Kp expression, our only gas here is oxygen, so it's just the partial pressure of oxygen cubed. So if our pressure of oxygen is remaining the same, oh hey, so is the Kp. So we increase the volume, which decreased the pressure. To increase the pressure again, our system needed to shift right and make more moles of gas. It's trying to get back to where it was. So it's trying to get back to the same pressure. So when we reach equilibrium again, pressure will not have changed, so neither will Kp. So the next one of these we're going to look at together is adding an inert gas. Well, adding an inert gas. That would be like a noble gas or something, a gas that's not part of our system, isn't going to react with anything in our system. If it's not part of our system, there's no shift. So everything's going to remain the same. So moving on from that, let's check out a temperature change. If we increase our temperature, well, temperature change depends on if our reaction is endo or exothermic. So let's take a look at this. We got a negative delta H. That negative delta H tells me that my reaction is exothermic, so heat's going to be a product. We are increasing our temperature, our heat there, so that's like adding more of a product. If we add more of a product, we're going to shift to the right. Or sorry, I don't know my right from my left. We're going to shift to the left. If we add more of our product, we are going to shift to the left. Well, as we shift to the left, that's going to use up some of our oxygen gas. So it'll be decreasing. If our moles of oxygen gas decrease, our volume and pressure haven't changed. So that means, our volume hasn't changed. So that means our pressure is going to be decreasing as well. Less moles of gas means we have a lower pressure. Well, Kp is only based off of our pressure of oxygen. So if its pressure lowered, Kp changes as well. And that's okay, because we're changing temperature. Temperature is the one time that your Kp will, in fact, change. So on this one, again, as we added that heat, that caused us to shift left. Left, we're going to be turning products into reactants using up some of our NO2, our moles of O2. If we have less moles of gas, we're going to have a lower pressure of that gas, and lower pressure of that gas, and our Kp will be lower as well. All right, last one real quick, adding more oxygen. If we add more oxygen gas, we're adding more of a product again. So that's going to cause our equilibrium system to shift left again. But it's trying to get back to where it was. So we want to know what happens once we reestablish equilibrium. If it's trying to get back to where it was, we're going to shift left until we have the same amount of oxygen that we had before. And if we have the same amount of oxygen, we have the same pressure of oxygen. If we have the same pressure, because that's the only thing Kp depends on, we have the same Kp. So we're going to shift left until the point where our moles of oxygen equal the original moles that we had. Moral of the story, our system is always striving to get back to equilibrium. So, on page 24, we have another free response practice question. This is a AP question that we got here. So what I would like you to do as we go through each part is to try this out on your own. And then we'll briefly talk about it together. So we're given this reaction up here. We're given our delta H, it's positive. The equilibrium is originally established by putting that solid NH4HS in a container. It's at 25 degrees Celsius. Some solid remains in the container, but some of it has decomposed into those two gases that we see to establish that equilibrium. On each of these, we're looking at the effects of different parts of our equilibrium system. So on part A, we want to know the effect on the partial pressure of NH3 whenever we add additional solid NH4HS into that equilibrium system. So based on what we've been talking about, Le Chatelier's principle and the few examples that you saw on number 3, go ahead and give this a go. Formulate yourself a little response for that, if you would, if this were a free response on a quiz or a test, and then resume the video to make sure that we are on the right track. On part A here, you should have found that there is no effect on the partial pressure of NH3. We're adding a solid to our equilibrium system. Adding solids and liquids have no effect on the equilibrium position. If our equilibrium position doesn't change, neither will our partial pressures of anything, because there's no shift happening. So let's take a look at part B. We're still looking for the effect on our partial pressure of NH3 gas, but now when we're adding additional solid H2S to the system. Okay, it's a solid again, but we got this little hint there. That H2S solid is going to readily sublime into H2S gas. So really, what's happening when we add more of that H2S gas? What effect will we have on pH and H3? Pause the video, give that a go, come back to check. you should find that your partial pressure of the NH3 is going to decrease whenever we add that H2S. Adding that H2S solid is really adding H2S gas because it readily sublimes. That extra H2S gas is going to cause our system to shift left. Well, shifting left to use up that excess H2S and get back to equilibrium is also going to use up some of the NH3. Using up some of that NH3, less moles is going to be a lower partial pressure of NH3. So that brings us on to part C. We're looking for the effect on the mass of the solid NH4S present and the effect on the equilibrium constant when the volume of the container is decreased. So again, give that a go, think it out, resume when you're ready to check. So our mass of the NH4HS should increase while K remains the same. So let's talk about that effect on the mass first. So we are decreasing the volume of the container, which will increase the pressure. Increasing the pressure means that we need to shift towards the side with less moles of gas, because then we'll have less gas particles in our system, therefore a lower pressure. That means we're shifting to the left. As we shift to the left, we're going to be producing more of our solid. Adding or removing a solid from the equilibrium system has no effect, but the amount of solid that you have in a system will still be affected by other shifts like we see here. All right, so then we have the part about K remaining the same. K is going to remain the same because K only changes with temperature. So when we have that shift left to get back to the same Kp or the same pressure that we had, we're going to shift left using up NH3 and H2S until they're back to their initial pressure values. Since Kp is just based off the partial pressure of those two things and they got back to where they originally were, it doesn't change. So that's the explanation we want to go into. Yes, we know K only changes with temperature, but make sure we know why. Those partial pressures are going to get back to where it was originally. That's why we're shifting, so we don't have to change that equilibrium position. All right, we got one last part here to try out. We want to know the effect on the mass of that solid and the equilibrium constant again, but now we are increasing the temperature. So try this out, resume to check. So you should find that your mass of that solid is going to decrease while K increases. So let's quickly talk about why. This is a endothermic reaction, so heat is a reactant. As we increase the temperature, we're going to shift towards the right. That shift right is going to use up some of our NH4HS. And that shift right is also going to cause our K to increase. As we shift right, we're going to be producing more of our products, more of both of those gases. If we have a greater partial pressure of both of those gases, that's going to give us a greater K value. So as always, making sure we're using the appropriate language within these free responses is important. So be sure that you are working on that when it comes to Le Chatelier's principle. Otherwise, equilibrium with our gases really just works about the same way as what we saw in Unit 6. So there you have it. See you next time.